My name is Jorge Vieira. I am a theoretical and computational plasma physicist. My primary research interests are in the areas of laser and beam plasma interactions and their applications to plasma-based accelerators and light sources. I am currently an associate professor at the Instituto Superior Técnico, IST, in Lisbon, in Portugal, and I do my research at the Group for Lasers and Plasmas at IST. I am the coordinator for the working group for theory and simulations for the EuPRAXIA preparatory phase project. I also belong to the EuPRAXIA doctoral network, where I am supervising a PhD student. And I am also the working group leader of an EuPRAXIA related project, which is called PACRI, the working group leader for plasma theory and simulations. So the plasma accelerators and light sources, they involve the motion of many particles, often in situations where relativistic effects, nonlinear effects, kinetic effects are very important. And so this means that theoretical models, purely theoretical models, are usually not available. And the computer simulations are also quite complicated because they need to retain all physical aspects that are relevant for these to model plasma accelerators, and the level of approximations that one can make is relatively limited. So these simulations are also complicated. So I guess that the field is quite challenging because many of the questions are complicated from a theoretical point of view, from a conceptual point of view, computational point of view, and also experimental point of view. So I think this all this all adds up to the complexity of the job, which often also involves a lot of compromises between different properties of the beams that you want to achieve. Yeah, so as I said, the purely theoretical models, they often don't exist. And so the only way to actually be able to understand the physics in detail is by performing plasma simulations. Plasma simulations are quite unique because they, unlike experiments, they give us access to time resolved and spatial resolved diagnostics of every quantity that we can think of in terms of the particles and in terms of the fields. So plasma simulations are quite important because of this. So they give us an answer. They'll help us to guide theoretical development by highlighting the relevant physics, and they also support experimental design because experiments are quite expensive still in our area, and so it's still cheaper and easier to do these simulations before the experiment. And simulations, they really work as a virtual experiment, so we can use them to test new ideas and see if they work. So I think the bottom line for the challenges of plasma simulations is the fact that they need to simulate a very large number of particles and their self-consistent motion, the fields that they produce in the presence of the fields of external lasers or external particle beam drivers. So I think the fact that this is a many-body problem, really many-body problem, is what makes the simulations so challenging. So this means that we need to use large supercomputers in order to be able to describe the physics in detail. Of course, because full-scale simulations with little or no approximations, they are very computationally expensive. A big area of research today is actually to try to develop reduced numerical models that still retain the basic physics that we need to capture and to describe with accuracy the evolution of plasma accelerators, but with the advantage that being much more computationally cheap. And so this is quite important in order to be able to do many simulations, parameter scans, etc., at a higher repetition rate, in order to find the best parameters, the best operating parameters for experiments, either future experiments or ongoing experiments.